Good afternoon. My name is Alex Chen. Welcome to this IAS Distinguished Lecture Series. Okay, will be given by Professor Tobin Marks. It's Tobin and me went back about almost 40 years. Okay, so when I was about the same age as you guys, right? Then we start to know each other, so start to really either work together or compete with each other for the past how many years, right? But then eventually, I think Professor Marks is one of the person I respect the most. Okay, so I think in the past June, okay, my group members celebrate my 70th birthday at Hangzhou. Okay, right? And many people ask me, so how come you still so energetic? Okay, still at the age of 70 can be so energetic. Then I said, because I have a role model, Professor Tobin Marks is already 80 years old. Right? So he's 10 years ahead of me. So I try to keep on running after him to catch up. Okay, right? So so this is a wonderful relationship, and it's not only as a dear friend, but also like my mentor and also teacher through the years, right? So Professor Marks got his PhD degree from MIT, okay, from I think the tutorage under Professor Cotton, okay, right? And then after that, right? And basically, he received almost all the award you can think of, okay, as a person, right? All the American, all the ACS award, the Catalyst award, the chemistry material award, inorganic chemistry award, whatever the award you can think of, right? And he also is a academy member, okay, for so many different countries, right? So we have colleagues that if you are the academy member of the Chinese Academy of Science, you think that you are great, right? Okay. He's more than maybe 10 or 20 of those academy members, right? So you can imagine, his recognition, okay? And most importantly, okay, not only he is a National Academy of Science, also a National Academy of Engineering, and also I think the Academy of Arts and American Arts, or something like that, right? So, and most importantly, he received the most prestigious National Medal of Science award. That's the highest award for scientists in the United States. Okay, and through the years, he has published more than I think 700 papers, right? Okay, and was about 218 papers, patents, right? And most importantly, remember this number, right? Okay, so Minglu, right? So professor's science, okay, spin off about 15 startups, right? And he generate, the sales, okay, from those startups, right? And then just give me a number, okay? If you said what kind of impact from the technology he developed and generate, the sale to all the society, just make a guess. How much money do you think? Yeah, just give a number. Yeah? Just 用中文跟我讲好了。how much money do you think the impact of the financial impact generated from his technology? No, because you may read those. How about you? Okay, 120 billion. Okay, okay, that means almost 1兆. Okay, 人民币. Okay, right? Okay, so can you imagine, the scientific impact of a person can generate about 1兆人民币 to the society. Okay, so. With that said, I think I don't need to read through all the awards he received. He just received so many awards. Okay, so the title of his talk is Application of Ductile Electronics, Strategies to Solve Matter Solar Cells. So, Tobin, please join me to welcome him.
First of all, let me thank Alice. It's a strange feeling to talk about solar energy, and I haven't seen the sun in the last week that I've been here. But I think there are tremendous challenges and scientific challenges and technological challenges, and that's what I want to talk about today. And let's see, I'm not familiar with this one. What happens if I do this? Okay, so we're going to talk about an idea that I've had for some time, a fascination. Can you make transistors and circuit boards and all of these things that would function under great mechanical stress? And if you really understand that, you might try solar cells. Could I make solar cells that are not brittle, that I could wrap around different objects? Just how far can I take it? And what sort of knowledge do I need to do that? And that's what we're going to talk about today. And we'll talk about solar. I mean, it's all around us. I mean, global warming, pollution by burning fossil fuels, escalating as societies increase in affluence, they use more energy. And another question is, how do we convince our citizens? There was a Chicago newscaster who said that the solar eclipse we had recently was due to global warming. So how do we also educate our citizens of how important these issues are and our politicians? And if you don't understand those issues, how can you grapple with them? And for solar energy, what are the economic, scientific, and technology barriers? So let me just shift gears a little bit, because this is going to be more of the central focus of my talk. And this is making electronics, optoelectronics that are ductile, that you can bend, that you can stretch, that you can fold. And if you can do that, you can do all sorts of wonderful things. And so you can see, you can do roll-to-roll manufacture. You can make yards of circuit boards. You can by printing them. And there's some examples there. And the right, it's making solar cells, printing them by the mile. And how do you do that? I mean, so it's not just to say, oh, just get yourself an ink and print it. But we need to understand a lot of science, because it'll probably require very unconventional materials. It'll push us to think more and more about the microstructure of polymers and how they respond to mechanical stress. So all of those things listed there, P&N type semiconductors, high-K dielectrics, tunable optical properties. If we're going to make a solar cell, we really want to maximize the ability of the material to absorb light. And we'll get into exactly how solar cells work in just a minute. And also a synergy between hard and soft matter. And by soft matter, I mean pliable things like polymers. And hard matter, I mean things like an indium tin oxide electrode. So this is the outline. We'll talk a little bit about how solar cells work and the challenges there. And then semiconductors, of course, solar cells, you'll see you use semiconductors, but I'll first introduce it from the standpoint of electronics, like transistors. And then I'm going to do something maybe you've never heard in a solar cell lecture before. We're going to do something which the pharma industry does all the time, to actually look at the cost of things and how you estimate the cost of things, to see which solar cell materials make sense economically and which don't. And then we're going to talk about new kinds of interactions between the molecules in the solar cell after we introduce how they work. And then we're going to get to the point to actually, I'll show an example of a solar cell material that I can take and do this with and still have efficient conversion of light to electricity. How that works and what we will do with it, we'll see a little bit of. But right here you can see some of the things that people are thinking about. If you could really make ductile, printable solar cells, all the kinds of things you never imagined before. You go on a camping trip, your tent is covered with a solar cell, so you can keep your cell phone charging all the time and talk to all your friends when you should be enjoying nature. So let's talk then about how a material that's called a bulk heterojunction material works. And I'm the type of person as a lecturer who likes to move around, so I'm doing my best.
Yeah, you want to use this?
Yeah, all right, let's try that. Okay, so this is a bulk heterojunction material. Imagine that I combine two kinds of spaghetti. And one kind of spaghetti, I really mean ramen if you want to, or mion, if you want to use that language. One conducts holes and the other conducts electrons. And I'm going to mix them together in a blend so that when I shine light on this mixture, it excites electrons in the one particular kind of spaghetti. And by doing that into the highest unoccupied molecular orbital, and I make electron hole pairs by this solar excitation. And this is just a picture, cartoon of what the bulk heterojunction might look like. And then what we're going to see is it'll generate electron hole pairs, and because of the low dielectric constant, it's hard to separate them. And we'll put them in an environment that facilitates the separation. And ultimately, the electrons will go to one electrode. And so you can see here, the electrons are going to one electrode. We have an interfacial layer that blocks holes from getting there. And on the other side, we have a material that collects holes and blocks electrons from leaking over. And so the design of these materials is very, very important. We need to create these kinds of spaghettis. We need green synthesis. We don't want to make toxic byproducts. We want to understand when I cast a film how these chains phase separate. We want to understand how, maybe I'll show another, let's do it, one other thing. I don't know how to go, let's see how to go backward. Yeah. So here's an example of some of the materials that are acceptors, and we'll say a little bit more about that in just a second. But this is a more physics-y picture, which ignores molecules. But again, it's something where here we've excited an electron. It forms this pair, which is called an exciton. It will drift through. This is the donor material. Here's the acceptor material. It will drift to the interface between them, and then the exciton will separate. And electrons will go one way, and holes will go the other way. And essentially, shining light on this material causes current to flow. And what I'm going to be showing you here is, this is the kind of data that I'm going to be showing you. So I've plotted the current density on the x-axis, on the y-axis, and the voltage on the x-axis. And so when this cell is operating, then you'll see we'll be generating curves like this. I'll get this. We'll generate curves like this, and this is the maximum power that can be generated. So this is the voltage that we create. It's called open circuit when the current is not flowing in that maximum current. This is the short circuit current. And basically, the number that you're going to see again and again is PCE, which means power conversion efficiency. And that's the power that the cell generates divided by the power of the input radiation. So what are some of the materials that we should be thinking of? What's out there? And on the left is silicon, and these are the power conversion efficiency. One is the lab, and one is when it's sitting on the roof of your house, and that's a cost of a panel. That would be a large element of the solar conversion. The silicon has been around for a long time. It's rigid, it's heavy, installation is very expensive. And the other thing which the advertisements never tell you, the lifetime of the systems are about 20 years. If you think silicon lasts forever, it does, but the whole device doesn't. There are inorganics which are creating a lot of excitement. Look at these perovskites. And a tandem cell is when I have two kinds of solar material working together, and the efficiencies that people are talking about are amazing. And Alex is one who's made a lot of contribution. That's Alex Jen, contributions to this field. We still have to overcome the toxicity of lead, the earth abundance, the durability, and that can mean sitting in air durability. It can also mean if they're, a hailstone hits them. On the other side, let's think about, we all know polymers. I mean, I hate to use this as an example, but these are made in billions of tons per year. So industry really knows how to make polymers and how to process them. Can we take all of that knowledge and apply it to solar electricity? So the advantage of these soft materials is high throughput, roll-to-roll manufacture, cheap earth-abundant materials. There are no toxic materials, like carbon, hydrogen, nitrogen, sulfur, mechanical flexibility. I mean, you'd love to have a solar cell that you could do this with. Tailorable properties. I can put electron accepting and donor groups, change the HOMO and the LUMO, do all kinds of things that you can't do with silicon, for example. Integrate with building materials. You don't need these elaborate framework. You just glue it onto the roof. Large open circuit voltages, strong optical absorption, which you can tune. You can make it absorb more near infrared light or visible light. Historically, the first cells had an efficiency of 3%, and everybody laughed, and it was sort of like a joke. But gradually, and again, Alex has been one of the major contributors here, the efficiencies are up at 21%. Durability, people say, oh, it's a bunch of organic, it'll just die. But very impressive work by Steve Forrest at Michigan, and he's been demonstrating at least approximate lifetimes of 30 years, which is really impressive. The cost, it's going to be hard for the inorganics to beat the kinds of costs of something that you can print, spread on a piece of substrate. And of course, it's so new and so different, we're certainly going to learn a lot of new things. So how far have the organics advanced? So these are timelines for donor polymers, and you can see they began in the mid-1995, and these are the donors. And we're also going to need acceptors, and there's been a revolution in terms of the acceptors. For a while, these fullerenes were I wrote a paper with Mark Ratner and Richard Friend. We wrote a paper showing you couldn't do any better than a fullerene. These nice tennis ball-like molecules. And then a guy named Xiaowei Zhang came along, and he made these really weird-looking molecules, and everybody laughed. They were flat. They were flat with sort of little arms sticking out, and everybody said, Xiaowei, this is ridiculous. They'll never get anywhere. And now the efficiencies are 21%. And we'll say a little bit more about how they work, and they pack completely differently than a fullerene. And that in itself is very interesting. So what are companies doing? Here's an example. Maybe you want a solar cell that's transparent in the visible, you can see through, but will absorb enough light in the other regions to generate electricity. So look at the size of these panels. And some of the challenges, I won't go through all of these, but just to give you sort of a sense that molecular understanding at the molecular and atomic level of how these work, how to stabilize these blends of the two different spaghetti strands that I mentioned, and maybe it's by adding a third kind of strand, engineering the blend interfacial electrical contact, and do all of this and have something that has a very high PCE. And so you can see the challenges on the left, and a lot of them are interfaces between very dissimilar materials and how to process them. And on the right are some dream applications. You can go camping, as I said, and your tent will generate electricity. Imagine a plane or a ship sinks, and they throw all these lifeboats, inflatable lifeboats, and they frequently have a canopy on them. Suppose this were a solar cell, so that you could never lose touch with people who are looking for you. So those are the kind of long-term objectives that people are working on. And now let me just say a little bit about transistors. And it's something we designed. We asked ourselves, here's an organic transistor. What would happen if, rather than having a contiguous film as the transistor element, instead that it was porous? And you might say, why the hell would you want to do that? But one of the things, of course, is it gives you more surface area, and this is called breadth figure printing. You can see it there. It basically is an evaporative process that leaves an organic film with holes, and you can make it by the mile. So it's very, very processable. You can vary the polymers that are used. You can vary the pore size. But the other thing about them is you can stretch them. So this is just showing one, and I won't get into the transistor function, but you can show that you imagine a metal wire you can't stretch, but a Brillo pad you can stretch a lot. And you can show by finite element analysis that these kind of porous structures actually dissipate a lot of the energy that otherwise would cause the material to rupture. And this is just some examples. These are micrographs, and you can see them stretching back and forth. And you'll see a number. So strain means how much we can stretch them. And you'll see plots where up to a certain extent they stretch and then they break. So here's some transistors, and what you see in the upper right-hand corner is the transconductance, which is a measure if you're going to build an amplifier with these transistors. It's related to the mobility, but you can see there that we're straining the device. So this is a transistor, and we put it in a device like this. And I was going to push the button here. We'll do that in a minute. But we can stretch them in different directions, and you can see this is the strain, how much it's stretched, and how little we've lost of the transconductance. And then this says, you might say, oh, but you've just stretched it once or twice. So this is stretching 10 to the fourth in this little machine here. And you can see how the mobility and the transistor properties are not lost. Pretty amazing. Let's see if I can get. Just to show you, but it's automated, so you don't have to have a graduate student doing 10 to the fourth stretches. So now I've shown you all these materials, and now I want to do, this is, I don't think you've heard a solar cell talk like this before. The pharma industry, when they're making a pharmaceutical, it may take 7-10 steps in the synthesis. What is it going to cost? And can we do that? And what we've done is we've done this for leading solar cell materials. So we're going to define something called the scalability factor, SF sub t, and it's really the sum of all the synthetic steps, the yield in each step that's reported in the literature, and the cost of the materials. And you'll see some surprising things. If you can start with a material that is dirt cheap, I mean, figuratively, if you have to start with, this wonderful solar cell material you've made takes 17 steps, and Alex has been in industry, you know that they just laugh at you. But even for a really good drug, it's not clear they want to do that. So the analysis is we're going to ask the question whether you want so many of the solar cell materials have halogenation on the different parts of the molecules. How important is that? How much does it add to the cost? And so the first step is looking at the building blocks and donor materials. We said donor and acceptor materials. So these are the building blocks to make the polymers that I showed you, or the small molecule acceptors. And so the input for each material is the number of synthetic steps, the yields of those steps, the market cost of the things you buy to make them, and ultimately the PCEs. And so the bottom line metric is always going to be the PCE, that power conversion efficiency, divided by this factor, the scalability factor. And these are some of the building blocks that one uses to make these solar cell materials. And so let's start by looking at halogenated versus non-halogenated, because you'll see in a lot of these materials, there's fluorine here, there's chlorine on some of them, and we know that affects the efficiency. But how much does it cost to have a fluorine there? And we're going to look at aromatics as well. And this is again the scalability factor. And what's interesting that we didn't expect, the building blocks for a lot of the aromatic compounds are very cheap, unlike some of the heterocyclic ones. And so we're going to say a little bit more about all that means. But halogenation significantly increases the scalability factor of almost all the thiophene materials, but has very little effect on the aromatic materials. So that's been a surprise. So let's now have scalability factor, and these are different families of building blocks. So these are donor families, and then this is the key metric, the PCE over the scalability factor. And so all of these are these quinoid aromatic ones, and some of them, and here you want this number to be as high as possible, the PCE to be high, the SF to be low. And some of them just jump right out at you. And when you're reading the literature, you really don't give a lot of thought to these kinds of limitations. And finally then, the last one then, these are the scalability factors of selected acceptors, and these then the PCE over the scalability factor. And all of a sudden, there are classes of materials that jump out at you. So halogenating non-fluorine acceptors definitely improves the PCE. When halogenation is applied to non-fluorinating acceptor materials, the SF is not strongly impacted. And this increases for halogenated non-fluorine acceptor materials, meaning it's more cost effective. So those are the kind of things that most of us don't think about, but if you're ever going to industrialize these, you're going to be looking for those kinds of numbers. So now let me talk about non-fluorine acceptors and a couple of surprises that we found. So one of them is people have spent a lot of effort to put so these crescent-shaped materials are called Y materials, Y6 materials, and there's been a lot of effort to put things around the periphery, mainly over here. We've done a lot of work here, others have, and over here. So we decided what would happen if you put acceptor materials in that juncture, and that had never been done before in a systematic way. And what we were sort of thinking of naively is you've introduced a dipole moment here. And what sort of effects would that have? And here's the synthesis, and we're going to always compare it against Y6. That's one of the champs of the acceptor materials for high performance solar cells. So we're going to compare, and you can see that there's no big difference yet. Another thing that our group has done a lot of is growing crystals and looking at the crystal structures, how these acceptor materials pack. And you can see that all of these new materials, these materials shown here this is the classic way that a lot of the acceptors that have been known pack, and that's not the way these pack. They always pack like this. There's more multidimensionality to the crystal structures. And this just shows film crystallinity, and we're always comparing to Y6, which is on the left, and all of these are much more crystalline. Mobility, here's Y6 on the left, and all of these guys are higher. Miscibility, so this is a polymer science thing, Schultz-Flory parameters, which allow you to say how much materials are going to phase separate versus being miscible. And you notice that all the new materials are over here, and Y6 is not nearly as miscible. So now let's look at the photovoltaic performance. And what's interesting, so the JV curves look not so different. We're always comparing to Y6, which everybody loves, or Y6 derivatives. And what you see here is all of these have very high fill factors. And that is a parameter that has to do with structural regularity and how long the excitons live. 80% is really, really high. And we don't understand why, all the reasons why. But what we see is that, or what we argue is that these electrostatic interactions, and I'll show you some more crystallographic information, when you put these tethers at this particular juncture at the top of the molecule, the right number of groups at the right place, the lattice contracts. And we think that's a very important point in getting these kinds of power conversion efficiencies. So there's strong dipole moments, and I think maybe I'll give you just one. Where is this one? Oh yeah, so this is very telling that if you look at the intramolecular interactions in these acceptors, you hit a sweet spot right here where you get the maximum contraction, and this is where we get the maximum power conversion efficiency. Okay, let me go on now. Let's get to flexible solar cells, and this is collaborative work with Yifang Wang, who was a visiting professor with us, and sort of by serendipity, she asked, people have mixed, to make solar cells flexible, they've mixed a variety of kinds of polymers to make the solar cell material, the active material, more flexible. And she picked chloroprene. And if you think people, for years, when they processed the films for solar cells, they added chlorobenzene, chloronaphthalein, and it was called a processing aid, a structure directing aid. But the last step in making the solar cell is annealing it, and all of that comes out. But suppose you had a chlorinated material, which is an elastomer. It's flexible. I mean, this is a very cheap industrial material. Cheap automobiles use this for the upholstery. It's called leatherette. It's very, very cheap, very durable. But suppose you had processing a type material that was not volatile, plus it gave you mechanical flexibility. What do you get? And this is what this study is about. And so here's some solar cell data. Very small. A couple of things that are interesting, and when I get to the mechanical properties, the stretchability, you'll see. But a little bit of this, adding CR means chloroprene, and in a minute we're going to try natural rubber, which doesn't have the chlorine, to see whether that has any good effect. And I'll tell you it doesn't. It's all detrimental. So you'll see that in a minute. But everything looks, the JV curves, this is the EQE, the quantum efficiency, everything looks pretty similar as you add more or less chloroprene. It's a blend. And the donor and acceptors This is the donor polymer. This is a classic, again, one of these crescent-shaped acceptors. And so everything looks good. We've done a lot of X-ray scattering, and the most important thing is all the parameters that matter, that are good. Let's compare. When I add more and more chloroprene, and this is this shows that, and then this is the stacking between the pi systems and the separation between the stacked pi systems. You see that adding the chloroprene does not have such a dramatic effect. Maybe the chains spread apart, but the stacking stays the same. On the other hand, with natural rubber, here's chloroprene, with natural rubber, then it really screws things up. That's not a physics description of what's going on. It causes aggregation rather than a more uniform blending. And so now we're going to look at mechanical properties. And what's amazing is you can add up to 50 weight percent chloroprene, and the PCE goes down only a little bit. And this is called the cracking onset is about 25%. So as you add the chloroprene, it gets more and more stretchable. And what you can see here, so this is stress versus strain. When you put stress on it, when does it break? And so these curves where it goes up and then stops means that it's broke at this point. Look at this one now. So you can maintain a lot of the power conversion efficiency, a lot of the electronic properties, and get this stretchability. And so this is Yifeng's cartoon, but now we've made. So what might be useful? So here with 5% chloroprene rubber, we still get 17% power conversion efficiency. And you can make stretchable devices, wearable devices where you charge them with the sunlight. And you can stretch them in different directions. This is 5,000 cycles, and you still have good photovoltaic properties. So CR, chloroprene rubber, is both the solid chlorinated additive that we've always added to improve the packing and phase separation properties of photovoltaic materials, but it's not volatile, so it hangs in there all the time. And it acts as a plasticizer. Plasticizers are things that prevent polymers from crystallizing. And a little bit can be very useful in terms of getting flexibility. And so this is just showing, this is the last topic. So those were, okay, forgive a graduate student or a postdoc. So very stretchable was replaced by hugely stretchable. And this is the last one, but what I'm going to show you then, and this is the structure of the solar cell. So it's got electrodes and active layers and all pretty much materials we know. It's the active layers that are going to be the key. It just shows here you can put it on your fingers and everything and go through all that mechanical stress, and it doesn't break or crack. And what you can see compared to the, competing materials is these are not so good, and this is good, and the same there. So there's one component that no one ever thought of before, which really is what's going with the key thing here. And the acceptors, these are the crescent-shaped acceptors, but what we did, so on the left are the two donor polymers, and on the right, we've taken the Y6, the classic one, but for these R groups here, we replaced them rather than just a hydrocarbon chain with a silicon in the chain. And you might say silicon is just a big carbon. What's the big deal? Well, if you think of think of it simple chemistry. Carbon tetrachloride you expose to air, It just sits there. Silicon tetrachloride fumes, and it's the ability of the size, the orbitals that are involved. And silicons also have interesting. They're very hydrophobic. Just putting that silicon there, and they can lower the glass transition temperature of lots of polymers. So if we combine all of that, and this is what we've done here, we've made a whole series, and the chain just has one silicon in it. And so let's look at some data. And again, I hate to always criticize Y6 or compare against Y6, but let's look, for example, the solar cell behavior. You put the silicons on there, it doesn't really change the band gap. It doesn't change the HOMO and the LUMOs. So here's Y6, and we're comparing. This is the donor polymer, and here's the silicon acceptor in both of these cases. And the power conversion efficiency is not so different until we apply mechanical stress. And then something really dramatic happens. And this just shows you on the left there, this is just this stretching machine, and we're gonna show more and more of that. But the acceptor by itself, and this is the interesting thing, the acceptor by itself, both acceptors with and without the silicon are fairly brittle. And this is just a micrograph showing if you stretch them enough, they start to crack. And the same with the donors. The chlorinated donor is a little more ductile than the non-chlorinated one. And this is the stretching at which point it breaks. But when we make the blends, these mixtures of the strands of spaghetti, something dramatic happens. So this is just showing also, we'll get to that in a minute, but this is just showing molecular weight of these different polymers and which point they break. And so you can see here, the one that has the highest molecular weight can be stretched the most before it breaks. And these are with PM6 donor polymer, and this was with the chlorinated one. Okay, so nothing there looks really so unusual or exceptional. But now let's go one step further. So the chlorinated one is intrinsically more ductile, but now let's make the blends, the photovoltaic blends. And this is some theoretical work, DFT and molecular dynamics. And one of the things you can look at just for the donors by themselves is the ones, look at the one on the right, which has a more wavy conformation. That means it's more stretchable. And you can see that all the way in the molecular dynamics. So if a polymer has a very rigid backbone, it's going to be much harder to stretch. And you can actually, with molecular dynamics, begin to calculate as you begin to stretch it, what happens. And you can also define something called toughness, and this is sort of how much energy is needed to stretch it, and how much energy is spent doing that. But let's look at, say, now we're looking at blends. There's a donor and acceptor, and look at the green one here. How much you can stretch it. This is the stretching in percent before it breaks compared to all of these others. So this is the one with silicon. And let's look at the crack onset. So you want this to be as low as possible. And so here's Y6, but all of the silicon ones are much better. This one, that one, and that one. And the tensile strength and toughness, again, Y6 is not very good, but the ones with the silicon are much lower. So what it's saying is that the blends are, when the silicon constituents are there, are much more elastic and tougher than with Y6, the sort of the one that everybody knows and loves, and it's an exceptionally ductile material. And so let's just finishing up now. So one way to plot it is, this is PCE. This is a map of every stretchable or unstretchable solar cell material that we could find in the literature. So SMA means small molecule acceptor, polymer means all polymer solar cell for donor and acceptor. And this is PCE, and then how much you can stretch them before they break. And you notice in the upper right-hand corner is the material I showed you, which has the silicon substituted acceptor. So it essentially, we've added an acceptor into this blend, which plasticizes the material, makes it more flexible. And okay, so now we're going to end here. So what we're showing you, the bottom is one that does not have the silicon substituent, and the top one does. These are two active layers of a solar cell. And I think I have to do this. So watch the top one. These are micrographs in case you wonder. So it's finally starting to break. So we can do that again if you want. So we've engineered into the blend the stretchability, this plasticization of the silicon substituted acceptor, and it really works. So and to the right, we've made mini modules, and what this shows for, say, for indoor light harvesting, what is shown in the upper right panel then, we're showing the current density that you can generate with various amounts of indoor lighting. And it looks pretty good. And you can make, in the middle, we're showing flexibility, we're showing making the film and not only bending it, but also twisting it. And the student decided we should also advertise that you can wash it with soap and water. So it's in other words, I guess if you want to wear your solar watch in the shower, it's okay. It's not, I don't know how much sunlight is in the shower. And again, just examples of wearables that are powered by the solar energy. Now I have to get out of this one. So some conclusions. Really, there's a really attractive sets of emerging design rules for making ductile organic semiconductors. And a semiconductor means it's something in principle you can use in a transistor or a solar cell. I didn't talk about hybrids of organic and inorganics. That's a different topic. But back on the third item, unconventional solar cells, beginning to control the organization of the donors and acceptors, the phase separation, dynamic dimensions and purity, scaling, and also to think about manufacturers, or to think about, well, what is this material really going to cost? And what tricks there are or devices to try to avoid that cost. And finally, for all of this, I've shown you again and again molecular orbitals, molecular dynamics calculations, DFT calculations. We're really living in maybe AI, machine learning. If you have lots of data, and some of these systems have lots of data, maybe they will help us envision the next step. So who did all this work? Some really bright, energetic young people. And so among these, some of you know Antonio Facchetti. He spent 30 years with me, and now he's a professor at Georgia Tech, and we're still collaborating all the time. And we have here people from all over the world, from Italy, from Taiwan, from China, from Korea, from Israel, from India, from New York. Some people would say that's a different world, a different country. And Turkey. I forgot Turkey. And also it shows we do not discriminate on the basis of age. And so it's a group that is very highly interdisciplinary. We're not all only chemists. We have chemical engineers, applied physicists, material scientists, and we do all kinds of stuff. And all kinds of stuff doesn't really sound really good. We're involved in lots of interdisciplinary projects and make research a lot of fun. And you can see behind us there's another shot of the campus. We're on a lake, a very large lake, and you can see there the Chicago skyline. This is our campus. We have lagoons, and you can see and swimming and beaches, and you can see the Chicago skyline in the background. This just gives you a list of all the people we've collaborated with, and Alex is up there. And these are the companies and agencies that have supported the work. So with that, again, it's great to be back in Hong Kong and back at City University. And thanks for your kind attention and hospitality. So thanks very much.
Yeah, so the floor is open for questions. Okay, any question? Want to take? Yeah, Shingo.
So very nice talk. Yeah, thank you so much for sharing the recent breakthrough work to us. So we always follow your work, but so you used a very short time to do a very comprehensive introduction, very inspiring. So I have one question regarding to the stretchable solar cell. So the mechanism you explained that is like this membrane structure of the molecular.
Right, and sort of the chain unwinding and sliding among each other and then coming back together.
Yeah, I think this is very smart and it's similar like the mechanics design for the the large scale electronics. Well, so this design is also very sensitive to the direction of the stretching. So in this case, so have you ever tested a different stretching direction?
Yeah. For the transistors, it's easiest to do. So we can stretch and measure in the source drain direction or transverse. But what we don't know is how the polymers unstretch, because it may well be that you think the strain is running this way, but in fact it may be like that, and so it will respond differently. We've done some finite element calculations with collaborators, and we really need to do more.
Okay, thank you. Another question is regarding to the I think this is the one idea. So I'm not sure. So if you pre-stretch the substrate and then you do all the fabrication of the materials on top.
We've done that also.
Okay. So can further enhance the stretchability, I believe.
Right.
Okay.
And also sort of observe it. What we will need to do, and some of that is going on now, is neutron diffraction. We've done lots of GWAX X-ray work. But the neutrons can see through metal. So we can see what's going on under the electrodes, for example, and things like that. And that should be informative. The question, so that we have several companies, we're waiting to hear whether the Trump administration kills all of the solar cell work or not. They will certainly pretty much want to kill these giant solar farms. But in terms of university research, we're very hopeful, and we're all writing our congressmen and senators. And so far, it looks like the basic research is going to survive, and the cuts that the Trump administration wanted to carry out are not going to happen. So we write a lot of letters.
Okay. Thank you.
To Trump.
Well, but to congressmen and senators, I mean, I think with the right advice, I know his main science advisor used to be a professor at the University of Oklahoma who studied hurricanes and tornadoes. There's a big center there, NSF. And I heard him speak, and he said, academics have too much report writing to do. It's ridiculous. We're going to cut that. And so that would be good. But if they cut the funding, you have nothing to report. That would make the reports very short. Yeah. We didn't have any money. We didn't do anything. Hopefully it won't get to that.
Yeah. Okay. Good. So any other question? Yes, Jimmy.
Yeah. Tobin, I really enjoy your talk, as always. Yeah. I have a simple question. Yeah, with so many chlorinated aromatic compounds in your structure, how can the stretchable solar cells be environmentally friendly?
I think the argument to make is the thickness of these films is like 100 nanometers, 200 nanometers. They're very thin. So when you spread it over, there's not a lot of chlorinated material. But, you know, there's an interesting PVC, polyvinyl chloride. For years, the chemical industry has said it's going away, it's no good, all of these bad things, it's still there because it's the best thing. All the pipes are made of PVC, plastic, because it's fireproof, for example, and very strong and very cheap. But someday, maybe and as you know, there's this big issue of fluorinated materials, so they wanted to ban all of them. And then all the physicians and biomedical people said, you can't get rid of this one or that one. Patients will die. And so they've now begun to modify the rules with some of the fluorinated materials.
Any other question? Actually, Professor Marks is just like a magician, right? Okay. Every time I thought, he's going to wind down in the organic semiconductors because he turned, last time you came here, you gave a lecture talking about develop some catalysts to do the recycling the polymer, right? Polymer termination, then try to get rid of all those used polymers, right? But then I thought you are not going to really work on this, right? So you are just like a magician, suddenly pull out a rabbit out of your head, right? Okay, so so this is, I think, also a very good lesson, okay, to all the young scientists, right? Because I have a lot of the postdoc students, right? They always argue with me, so they really need to get a very high efficiency in order to certify, then in order to publish in good papers, right? Publish Science or publish in Nature paper. But look at this, right? Okay, with a PC about 15%, you still manage to publish in Science, right? Okay, and it's all related, okay, about what kind of good story and insight, okay, into your system and give a very nice story. Maybe you can comment a few on that, something on that.
Someone once, first of all, always listen to your students. Sometimes they have a crazy idea and it may actually work. And be open to those kinds of things. Someone once defined creativity is taking two things from a very dissimilar area and bringing them together. So Yifang had this idea of using chloroprene, and we talked, and I said, I don't think it'll work, but it might work. And she was also very, very persistent. And then you started saying, well, wait a minute, isn't this the chlorinated additive that everybody adds to process their solar cell, but then it evaporates when they anneal? And maybe you lose that effect. What would happen if you could keep the chlorinated material in there and it was elastomeric at the same time? So some of it is you're getting results to think about what story it would make.
Yeah, so if you really look at your CR, that's a chlorinated double bond polymer, right? Okay. Then if you look at that, that's just one double bond compared to PVC, okay, right? Okay. Right? And then if you look at the PVC, it's a very crystalline material. Right. But then just introduce that double bond, then it become, just like rubber. Okay, right? So this is something I really encourage all our students, right? Don't be just be trapped within just a very small area. And sometimes you really need to think bigger and think about some of the new phenomena. How do you explore those kind of things and try to add that component into your research? Not everybody is really have to compete for high efficiency, right? Okay, it's all related to some good story you can tell, and also some insight you can provide in your science. Okay, so I really encourage everybody to do something like that. Okay. Yeah.
I was just going to say the editor of Phil Ball, I think the editor of Nature at one time said that Nature has a very high impact factor, but he said it's only 10% of the papers in Nature that give the impact factor. The others were all fine papers, I have science papers that hardly have any citations. Nobody seems to read them.
Yeah. So, any other question? Yeah, me.
Thanks for your very nice talk. I want to talk. I want to ask, why do you choose the honeycomb structure in organic transistors? Is it possible that we introduce this honeycomb structure in organic solar cells?
Okay, first of all, for the transistors, we were making electrochemical transistors. And so those are ones where they can generate a huge amount of current because you have a doping of the polymer. It's not just, it's another lecture, but it means you've changed the structure. It's like polyacetylene or doping it. You generate more carriers. So then we thought of that. Then if you have a porous structure and you want to be able to switch back and forth, that's a tremendous advantage. And then we thought, hey, the porous structure ought to be much more stretchable. For the solar cells, that's an interesting idea because it's giving you, it may give you a new type of bulk heterojunction structure by having a porous polymer. Somebody ought to try that. It's a very good idea. Congratulations. She's already working on a patent application. No, it's really intriguing. I don't know whether that would work or not, but do you guys,
Actually,
does she work for you?
Yeah, she worked for me, and actually, she is very good. Okay, in always come up with some ideas, right? Quite different from others, right? Okay, so
you know,
so with some very good observation. So I think so. Continue to dig like that. Okay, and one thing I also observed, right? Can you go back to your the picture of your group, right? Okay, then you talk about your the component of your group is you have undergraduate, graduate, and also postdocs, right? And then I just also to take this opportunity to encourage all our younger students. Xingying, you are just a graduate and then ready to get into your graduate school, right? Okay, right? So you belong to bottom of the food chain, but then you can really exercise to really contribute to really high impact research. Okay, so I think.
Yeah, going back to that suggestion,
Yeah.
if you want to collaborate on that, we know how to make the porous materials. We can send some to you to make a solar cell or do something like that. That would be fun.
Yeah. So continue to do that. So I think your picture actually brought me back to some of the good old memories when I was in Seattle at the University of Washington with my groups. Okay, so yeah.
Similar weather to out here.
Okay, good. So if no further question, please join me to thank the Professor Tobin Marks.
Thank you very much for inviting me. I was looking at this and saying, now I've got to pack it up and put it in my briefcase. Then I remembered it belongs to you guys.
Oh, yeah. We have some souvenirs to give
Oh, thank you.
and also some pictures to take together. So who's going to take pictures?
Sorry.
Okay, thank you very much for the wonderful. Okay, always bring up. So
Just right, you get it.
Okay, 3, 2, 1, and then 3, 2, 1, and then 3, 2, 1. Okay.
Can we have one more?